Okay, guys, sorry about that. I got interrupted by someone from my family. We were up to taking care of the second data point. This is video 3 for chapter 17. So the second data point is the value of the pH after 10 milliliters of sodium hydroxide has been added to the solution of 50 milliliters of 0.1 molar acetic acid. So if we go back to our graph, which you should kind of be making at the same time, now we've got this point, 2.88, and now we have 2.17, okay? Next point is going to be 25, then 50, then 60. So here comes 25 milliliters, okay? The total volume of the solution now is going to be 75 milliliters, so we're going to take care of that in a second. This is going to turn out to be a special point in the titration because we've already calculated that the end point is 50 milliliters. Remember that? Back here, we've calculated that the end point is 50 milliliters. So 25 is called the half equivalence point. So we're going to go through the math, but in the end, we're going to see that this special point, the pH, is equal to the pKa. Okay? So I'm sorry, this one down here. So let's go through it one time, and then you can save time on the test when you have one of these. Okay? So if I add 25 milliliters of sodium hydroxide, first thing I always need to do is calculate the moles of the titrant and the moles of the material that are being titrated. This hasn't changed throughout the whole exercise. 0.1 molar sodium hydroxide times 25 milliliters of sodium hydroxide changed to liters gives me 2.5 times 10 to the minus third moles of sodium hydroxide. How many moles of acetic acid I have? Well, that's what's in the beaker at the bottom. Same every time. 0.1 times 50. Make these guys a little easier to see. Okay. 0.1 times 50 milliliters in liters is 0.05. So this times this gives me 5 times 10 to the minus third. So see how this is half of that? That's going to come up in a second. Okay, first thing we do, neutralization. The added sodium hydroxide reacts with the acetic acid to make acetate and water. Neutralization, reaction of an acid and a base to make a salt and water. Before the neutralization happens, I have these two initial quantities in moles, okay? Do the stoichiometry, not the equilibrium. This is not an ice box, okay? So all of this material is going to react. Why? Because this is half as much as this. So this goes from 2.5 times 10 to the minus third down to 0. Okay, what happens here? This starts out at 5 times 10 to the minus 3. Half of 5 is 2.5, right? As this guy uses up 2.5, you use up 2.5 here, so 2.5 is left. Does that make sense? So if I did a minus here, both of these would be minus 2.5. So 5 minus 2.5 gives you 2.5. 2.5 minus 2.5 gives you 0. Okay? How much acetate do I have? Well, the stoichiometry is 1 to 1. So every one of these that I start with, I end up with one of those, and we don't care about the concentration of water. Next step, always after you're done with the neutralization reaction that you do in moles, get the new molarities. The new molarities are these two answers, and now dividing by 0.075. Why 0.075? Because the total volume of the solution is 75 milliliters, 50 that was originally there from the acid, plus the added 25 that you just put in. Notice these two concentrations are identical, just like the two number of moles were. Okay, next thing you have is you have an acid and its conjugate base in solution, so you have a buffer. So you want to know the pH of this buffer solution. How do you do that? Well, you do the hydrolysis reaction for the buffer. Easiest way to do it is with the HAC reaction. So the acetic acid reacts with water to make acetate and hydronium. You start out with 0.033 here. You start out with 0.033 here. Those are just from here. You don't have any hydronium yet, right? It's 10 to the minus 7, but that's basically 0. This guy goes down by x. This guy goes up by x. This guy goes up by x, 0 plus x is x. The x next to this number is so small that we can ignore it. So this is a little approximately sign, approximately. And believe me, it's very approximately. It's not even 0.032999, okay? It's going to be so close to that. All right, plug these into the equilibrium expression. That's on the next page. Here's the Ka. Ka is equal to the X. That's the hydronium ion concentration. This is the acetate concentration divided by the acetic acid concentration. All I did was plug in those numbers there. Okay? Products over the reactant. Solve for X, right? Solve for X. Amongst other things, X is equal to the hydronium ion concentration. That's back here. X is equal to hydronium. Hydronium will give you pH. These two numbers, guys, cancel out. Look at that. Same exact number in the numerator and the denominator. X is equal to hydronium, which is equal to Ka. So two ways of looking at it. The pH is equal to the pKa at the half equivalence point, or hydronium is equal to Ka. So hydronium is equal to Ka at the half equivalence point. So how do I get the pH? Just like I would have got the pKa. Anytime you want the P of something, you take minus the log of that number. So take the log of this number. You're going to get 4.77 with a negative sign in front. Then drop the negative sign because logs are always going to be, pH is always going to be positive. So the pH in the end comes out to 4.77. So just to do that one real quickly, pH is equal to minus the log of 1.7 times 10 to the minus fifth. The log of 1.7 times 10 to the minus fifth will come out to negative 4.77. And then pH, negative times a negative is a positive, you're going to get 4.77. Okay, that's the third point. Special point called the half equivalence point. Special point called the half equivalence point. Okay, let's go on to the fourth one. Before I do that, let me go back to here to just show you. Look how flat that is. We added an extra whole 15 milliliters of 0.1 molar sodium hydroxide, which is pretty strong. And I only got this to go up by 0.6, right? It's highly buffered in this region in here, especially between here and here, especially right around here. Okay, the next point. Remember, this is a special point called the equivalence point. Right? The equivalence point was 50 milliliters. So, helps to know that before you start the problem. To do part D, you want to calculate what is the pH after 50 milliliters of sodium hydroxide has been added. So, you can go through the same steps. Right? You have 50 milliliters of sodium hydroxide. You happen to also have 50 milliliters of acetic acid to start with. So do the calculation to get the moles of the two reactants. 0.1 times 0.05. How come this is 0.05? Because 50 divided by 1,000 is 0.05. And I get 5 times 10 to the minus third moles of sodium hydroxide. The amount of acetic acid hasn't changed. It's the amount that was originally in the beaker. It's 0.1. Sorry, that was hard to see. 0.1 times 50 over 1,000. It's 0.050 liters. And I'm going to get 5 times 10 to the minus third moles of HAC. Okay? All right, neutralization reaction you do in moles. Before the two react, you have 5 times 10 to the minus third of each. They're in equal molar amounts. They both neutralize each other. So in the end, I use every bit of this up and I use every bit of this up. So they go down to 0. This guy goes up by the same amount that this one went down. For every one of these that's used up, I create one of those. So that goes up by that amount. And water we don't care about. Okay? So in the end, I no longer have any HAC left over, so I only have to, this guy went down to 0, so no reason to calculate its molarity. So I have at the end point a solution of just acetate ions. Those acetate ions are going to act as a weak base, and they're going to drive the pH a little bit higher than 7, but let's calculate how much that is. So the acetate ions, before they start to react, take their take the number of moles here and divide it by 0.1. Why 0.1? Because 50 plus 50 is 100. You're at the equivalence point. You've added 50 milliliters of sodium hydroxide to the 50 milliliters of acetic acid that you originally had. So the new volume is 100 milliliters, which is 0.1 liters. Okay, so that changes this to 0.05 molar. Okay, all right. Now I have the hydrolysis of the weak base. I don't have any HAC, so I wouldn't want to write it the way we wrote it the last time. We've been writing for points B and C, we've been writing it for the hydrolysis of the acetic acid. But since I don't have any, that would be silly. So I have to turn this around for the hydrolysis of the acetate. So acetate, when it reacts with water, makes acetic acid and removes a proton from water to make acetic acid and hydroxide. This is 0.05 because that's what we had after the neutralization. It's going to react with water. We don't care about the concentration of water. We don't have any HAC anymore. All of it was used up in the neutralization. I'm going to create a little bit of it from the reaction going backwards, a tiny bit. And this is also 0 because I don't have any hydroxide. All the hydroxide was used up. It went down to 0. Okay? 0.05 minus X gives me 0.05 minus X down here, but I can drop the X because it's going to be very small. Okay? This Kb, you're going to see it in a second, is 10 to the minus 10th. Well, that's a tiny number. So you can definitely drop from 0.05. This is 10 to the minus 2. This is 10 to the minus 10th. That's 8 orders of magnitude. So there's no question X is small next to 0.05. So we can drop the X here. Okay, don't drop the X here because it's not being dropped from something. It's being added to 0. So it's very significant. Don't drop the X here because it's also very significant. You're adding it onto 0. It's only can drop the X when it's added or subtracted from a big number, like here. Okay. How do we get the Kb for acetate? Kb for acetate is equal to Kw for water divided by the Ka for acetic acid. So that comes from Kw is equal to Ka times Kb. We want Kb. We have Ka and Kw. So Kb is Kw divided by Ka. So I did that here. You had Ka throughout the whole question already. Okay, do the math. This comes out to 5.88 times 10 to the minus 10th. Okay, going back up to here, Kb is equal to x squared divided by 0.05. Solve for x. So how do I do that? I take this number times 0.05 and then take the square root. X, among other things, is the hydroxide ion concentration. Look at what X is. Hydroxide ion concentration at equilibrium. So once I know what X is, it's 5.42 times 10 to the minus 6th. I can get pOH by taking the log of this number and dropping the minus sign. The log will come out to negative 5.26, so the pOH is 5.26. Okay, last step. Nobody asks you what hydroxide is or what pOH is. They want to know what pH is. So how do I get the pH? 14 minus 5.26 gives me 8.74. That is the pH at the equivalence point. The equivalence point is 50 milliliters. So I have my second to last point on my sheet. Go back to the table. Okay, right here, this is the equivalence point at 50 milliliters. 50 milliliters is the point when I've added just enough sodium hydroxide to neutralize all of the acid. All the HA is now gone. It's been driven over to AC minus, and AC minus in solution hydrolyzes with water and makes the water have a pH that is slightly higher than 7. 8.74 is slightly higher than 7. Okay, one last point. It's going to turn out to be trivial, okay, or a little bit easier, right? We're not going to have to do one more hydrolysis reaction, and I'll show you why. Because it turns out we're going to have 2 bases in solution when we're past the equivalence point. Okay? All right, so what's going on? We are now past the equivalence point, right? So let's do the first 2 steps, and we'll see what's going to happen in a second. Okay, so first step always, calculate the moles of the 2 reactants. You're adding 60 milliliters of sodium hydroxide from the burette. 60 milliliters is 0.06 liters times 0.1. That gives you 6 times 10 to the minus 3 moles of sodium hydroxide. For all 5 steps, this second one has been the same. Concentration of the acetic acid multiplied by its volume, 50 milliliters, turns out to be 0.05. I'll make these a little darker. This comes out to 5 times 10 to the minus 3rd moles of acetic acid. Look, this is the first time the sodium hydroxide is more than the acetic acid. Last time they were equal, so this time I'm going to wipe out all of this, and I'm going to still have 1 times 10 to the minus 3 left over. So here we go. Before the 2 react, this is 5, this is 6, this is 0, this is 0. After they react by going all the way to the right, this guy goes down to 0. 5 out of 6 get used up here, right? When this guy goes from 5 to 0, this guy goes from 6 to 1. This guy grows in at the same rate that these 2 disappear at. So this guy goes down to 0. This guy, only 1 is left. And how much do you have over here? You started with 0, you go up to 5, right? Stoichiometry. For every one of these that I use up, I create one of these. Which is the limiting reagent? The acetic acid. I have leftover hydroxide. Last time, these 2 things, I used them up in equal molar amounts and had none of them left. Now I have a solution with 2 bases in it. The strong base hydroxide and the weak base acetate, okay? So just for the thing, it's going to turn out, guys, that this number right here, you could just take that number and get the pKa, and then from the pKa, get the pH. But let me show you why that works. Okay, for first step, let's take care of the dilution. After the neutralization reaction, you always take care of the dilution. I have a total volume of 110 milliliters of solution. How come? I have 50 from the acid and 60 from the base to make 110. So how much hydroxide ion do I have before it starts to react with the water? Okay, if it even does a reaction with the water. So this is going to be 1 times 10 to the minus 3 divided by the volume. 110 milliliters is 0.11 liters. That comes out to 9.9 times 10 to the minus 3. How much acetate do I have in solution? AC minus. I have my leftover here. 5 times 10 to the minus 3 divided by 110 milliliters in liters gives me 4.5 times 10 to the minus 2nd. Okay. The hydrolysis reaction. Let's see if anything could happen. If I have the hydrolysis reaction and I pretend, what can the acetate do, right? The acetate, okay, a little tiny bit of it can react with water. Certainly can't, these 2 things can't react with each other. They're both already bases, but a little bit of this might be able to react with water to make a tiny bit of the acetic acid back and more hydroxide. Okay, so let's see any more hydroxide we can make. So if this guy has to go to the right because there's no HAC this time, there's plenty of hydroxide, right, from up here. All right, but since this is 0, I'm going to make a little tiny bit of it back. So if somebody asked you to calculate HAC, you could. Going to be tiny, okay? This guy has to go down by x, this guy has to go up by x, this guy has to go up by x. This is 5 minus x, is 5 times 10 to the minus 3. Since there's so much hydroxide in here, this reaction is not going to go very far to the right, and x is going to be small, so we can drop the x from here. This is 0 plus x is x. This is 9.9 times 10 to the minus 3 molar plus x, but I'm telling you, x is small. So net relative to a 9.9 times 10 to the minus 3, x is going to be something like 10 to the minus 5th, 10 to the minus 6th, 10 to the minus 7th. It's going to be insignificant. So an insignificant amount of additional hydroxide is formed in the hydrolysis, because if x is small here, it's certainly small here. So from up here, you could have been done. You could have calculated pOH from the amount of hydroxide left over after the neutralization, and that would give you a pOH of 2 and a pH of 12, because 14 minus 2 gives me 12. Okay, another way of looking at it, we are going to calculate this just to see, because this guy was insignificant, but with this number and this number, we can calculate the amount of HAC that's in the solution at very high pH. Okay, there is a little bit, but we're going to see that number is going to be tiny. Okay, probably smaller than any other numbers that we've seen. So this was, X was an insignificant amount, so you can just go with that number, right? Go with that number. 9.9 times 10 to the minus 3 is basically 1 times 10 to the minus 2. That's how come you get a pOH of 2, right? Take the log of 10 to the minus 2, you get negative 2, so pOH is 2. All right, let's read this note here. That acetate can't react with the hydroxide because they're both bases, okay? So that's the only reaction that can occur. Okay, so just out of curiosity, if somebody said at pH 12, how much HAC is around in the solution? How much HAC do you have? Well, you can do that from here, right? We know this is the concentration of hydroxide when the solution is pH 12. We know what Kb is from the last one, so let's go ahead and put those guys in. Kb is equal to the concentration at equilibrium of HAC. I don't even have to write X. I'm going to write that times this, 9.9 times 10 to the minus 3, all divided by 5.0 times 10 to the minus 3. Okay? And from part D, I'm just going to look up Kb. The Kb value, remember, super tiny, 5.88 times 10 to the minus 10th. Okay? All right, so 5.88 times 10 to the minus 10th is going to be equal to, this guy's coming up, 5.0 times 10 to the minus 3. Right, this guy's going to come up here. This guy's going to go down here. 9.9 times 10 to the minus 3. And that will give me HAC. That should be right. Okay, do that calculation, and you're going to see the amount of free acetic acid in the buffer solution after the equivalence point. How far after the equivalence point? 10 milliliters after the equivalence point when you got all the way up to pH 12. Okay, so I'll do the math now. Okay, I get 2.97 times 10 to the minus 10th. So you can see that's X, right? That's how much of this I grew in. 2.97 times 10 to the minus 10th is tiny next to 10 to the minus 3 and 10 to the minus 3. So of all the numbers we've been working with, boy, you really can drop the X from there. Okay? And that's how much free acetic acid I have at pH 12. Hardly any. It's all driven over to AC minus by the huge amount of base that I have. So all in the buffer solution between sodium acetate and acetic acid, it's all acetate at pH 12. Okay. That is going to conclude the buffer problem. Did it in two parts. And I just want to show you, go back to this graph. Now we have all 5 points on it. This one is after the endpoint, at the endpoint, halfway to the endpoint, special place called a half equivalence point. Another point, buffered here. Here's the initial solution. So this really is unbuffered. In order to be a buffer, I need to have both HAC, significant amounts of HAC and AC minus. I don't have that here. I don't have that here either. Here I have all AC minus. Here I have all HAC. But through here, this is the sweet spot when it's very buffered. I have significant quantities of both the acid and its conjugate base. So during the titration of a weak acid with a strong base, it's buffered for the whole first part of it. Good. All right, guys, the last thing I'm going to show you on this video is a bunch of stuff that we're going to skip. So in the notes for chapter 16, I'm not going to cover on the test or ask you any questions about normality or equivalence. You don't need to think about it in those terms in order to do the questions that we need to do. So that covers 15, 16, 17, and 18 of the notes, actually, and 19 of the notes. So I'm going to pick up for the last video for chapter 17, I'm going to pick up on page 20, which is talking about solubility. Okay? So we should be able to, this isn't that much, so we should hopefully get through this in one lecture, just 10 pages. Okay? All right. Signing off.